All right, good day. Today, let's have a look on this section called the statics. So under that section, we're going to have consider the subsection called the beams. So I just took this question from this question paper dated April 2025. So as you can see here, even though that in this question is not that clear, but I'm not sure if this 25 kg per m is for the mass of the beam, or we're having the beam, this black thing that you see here, maybe this black thing is the beam, and then on top of the beam there is a uniformly distributed load. So it's not clear. It's not clear if this black thing represents the beam, and then this thing here, it represented the load being placed on the beam. So sometimes they clearly specify that. Okay, but it doesn't really matter. It don't affect the solution. It's fine. Maybe let's take it that the beam, or let's say that this thing is going to be the mass of the beam, or it's the mass of the beam plus whatever that is placed on top. Okay, the first thing that you have to do here for calculation purposes, we're going to convert the uniformly distributed load, as you can see here. For calculation purposes, a uniformly distributed load can be taken as a concentrated load or point load. So we're going to convert that uniformly distributed load to point load. Then after converting that, as you can read here, you can calculate directions and bending moment by representing the UDL as a point load. And that point load will be placed at the center or at the midpoint of the UDL. So like this, now we're going to change the point load, the UDL to point load. So instead of having the point load, instead of having the UDL, we're going to have the point load. And then we have to put that at the midpoint as well. Oh, now it's going to be challenge here. Yeah, okay, when you check here, total length of this beam is 10 meters. So from here to there is 10 meters. 5 meters, it was supposed to be halfway. So when you check 5 meters, it was supposed to be somewhere here. But when you check according to this sketch, 5 meters from here to there. So that's why I'm saying that there's going to be now a challenge. I'm not sure which one to use now, to use my own. Should I take the 5 meters from here to there, or should I stick to that 5 meters from here to there? Okay, let me try to rectify it. But that's how you will get this thing from the original question paper. uh, I think in the middle it will be somewhere here. and 5 meter will be from here to there. Yeah, let's stick to that. Yeah, so now we change that point load. We change the UDL to point load. We are going to put that point load exactly here at the midpoint, so which is here. So we put it halfway. Half of 10 is 5. So this force is going to act here halfway. Then the magnitude of this force, which is the total force of this total weight of this beam, you will get it by saying 25 multiplied by, remember this 25 is in kg, we have to convert that to 9 to your weight, then you multiply by 9.81, and this will be the weight per meter length. So now we wanted the total load. So to get the total load of this beam, you take that weight for 1 meter length, you multiply it by the total length of the beam. So which is going to be 25 multiplied by 9.8 multiplied by 10, 2450 Newton. Good. So I'm just going to, yeah, what I did there is this statement here to calculate the total load, to calculate total weight of the UDL, multiply the weight per meter length by the length over which the load is spread. So I just applied this statement to convert the UDL to point load. I multiplied the weight per meter length by the total length over which the UDL is spread. Now, actually I was supposed to use this diagram here, but let me quickly do that. We said that force will be here. With the magnitude of 2450 N. Right after converting that UDL to point load, now we can proceed with calculating the reactions. So we're going to take moments at point M, which is this. So take moments at point M. So we know that to have the state of equilibrium, the clockwise moments should be equal to anti-clockwise moments. So if you are here at M, if you assume this is your support or fulcrum, when you apply a downward force like this force together with this force, they will tend to bend this beam like this. they will tend to bend this beam in that manner, which is kind of this movement which is going to be clockwise. So this force together with this force, they will try to bend this beam in this direction, while this upward force here uh, will tend to bend that beam in an anti-clockwise uh, direction. So this force here, so if you fix this thing here, when you push this thing upward, this thing will tend to bend in this way, so which is anti-clockwise. So under clockwise moments, it means that we're going to have this force and this force. So we'll take those forces and multiply them by their distances, which is what we call the moment. So taking moment at point M, the first force that we are going to have will be that red force, so which is 1450 multiplied by the distance. The distance will be from point M to this force here. As you can see, it's 5 meters. So you multiply this by 5. Multiply by 5. Plus we go to the next force. The next force, it's 40. Then multiply by perpendicular distance. The distance from M to 40, it will be 10. So here's the 40 that I've been talking about. So the distance from 40, from M to 40 is the total length is 10. Then that's all for clockwise moments. Then I said that for anti-clockwise moments, we're going to have that upward force, which at the moment is unknown. We don't know. We'll take that force, multiply by the distance from M to that force. So the distance from M to that force of N to here, it will be 8. Remember, you will get it by saying 10, which is this total length, 10 minus 2. So 10 minus this 2 will give you the remaining distance will be 8. So that's where this 8 is coming from. Then from there you make n the subject of the formula. So when you make n the subject of the formula, you will have n equals to n is equals to hopefully 1581.25 Newton. So that is the reaction at that point. Now let's take moments at a different point to get the other unknown reaction. Now we move to taking moments at point N. So we're going to take moments at point N, which is this one now. So when you are at that point, if you assume that this N is the support of the fulcrum, or if you fix that thing there, when you push this thing from this side downward like that, this beam will tend to rotate or to bend in this direction, which is clockwise. Then even this upward force there, when you push this thing from this side, it will also move like that. It will also try to move or bend like that, which is from here to there, it will be clockwise as well. So for clockwise, we're going to have this force and that force of 40 there. Then under clockwise, you'll have those forces. So the first force is 40. Multiplied by the distance from N to 40, as you can see, is 2. From N to 40 is 2, plus that other force at M, which we don't know at the moment. We don't know direction force at the moment. Multiplied by the distance from N to M. So from N to M is the very same distance that we've seen before. From here to there is 8. So you multiply this thing by 8. Then that's all for clockwise moments. Anti-clockwise moment will be this force here. So if you push this thing like that, if it's supported here, assuming that this thing is not supported here. So if this is your fulcrum, this thing will bend or will try to rotate or bend in this manner due to this force here, due to this force. Then from here to there, as you can see, it will be an anti-clockwise rotation or bending. So under that anti-clockwise, you are going to have only that force. It will only be that force. So it will be that force of 2,450 multiplied by distance. So the distance that we're going to use there now is going to be the distance from here to that force to where we're taking moments. So this distance will be how much? You can say 10 minus 5 minus 2. It's going to give us 3. So the distance will be 3. Multiplied by 3. Then you can see M is unknown. Then you can find M. Make M the subject of the formula. M will be equals to 908.75. Those are the reactions, and that means we've answered the first question at 3 marks. Now we move to the next question, which is to draw the shear force diagram. So to draw the shear force diagram, we come to this. Okay, on the shear force diagram, and then maybe before that, what is shear force diagram? What is shear force? Shear force, here's the definition of the shear force. Make sure that you know it, as it normally, okay, let's say sometimes they will ask you to define it. So the shear force at any section of the beam is the algebraic sum of all the forces to the left or to the right of the section. We'll see that. And then the bending moment, okay, we're not yet at the bending moment. Okay, when drawing the shear force diagram, we start from the left-hand side and move to the right, and then we're going to follow the directions of the loads as well. So sometimes as we move to the right, we're going to move upward, downward, to the left. So that will be determined by the forces as we move to the right. So as we know that we have two types of loads. So on the shear force diagram, a point load will be represented by a vertical line. A point load will be represented by a vertical line. So let's go to the shear force diagram. So let's start here. So if you start from the left, which is here, you can see that we are going to have, at this point, we are going to have an upward force. So we're going to have an upward force, and that upward force is point load. Then we said that the point load will be represented by the vertical line. So this vertical line now will be upward. Why? Because this force is acting up. So this force of 908.75 is acting up. That's why we draw an upward line, a line going up. And then this line is going to represent this magnitude of 908. You have to indicate these values here. So you will write 908 here, 908. 0.75 Newton, 0.75 Newton. Right, when you draw shear force diagram as well as the bending moment diagram, make sure that you show these values. Right, from there, oh, this is okay, it's fine. This is that diagram of showing us the 5 meter not being at the midpoint. So what must I do? Let me try to rectify it as well. Right. When we draw the shear force diagram, you must construct these vertical lines, these dotted vertical lines, as you can see them going down. So where do we draw these dotted lines? It's a good question. Where to put them? So you will put them where there is a point load. Then when we check here on this diagram of ours, we have a point load here. That's why we have this line. We have the point load here. That's why we have this line. We have the point load here. That's why we have this line. That is point number one. You put these vertical lines where you have the point load. You also put them at the beginning and at the end of the UDL. So the UDL starts here and ends here. And there is already those lines are already there, then it's fine. And then we must also put this dotted line at the point where the shear force diagram crosses the horizontal line. But we'll see that at the later stage. So let's finish the shear force diagram first. And then we'll see where this shear force diagram crosses this line. And then where the shear force diagram crosses this line, we're going to make another vertical dotted line. Right, as we said that we are going to follow the directions. The point that I was trying to show is that here we don't need the dotted line going down. Since here there is no point load, here. So remember that point load that we put, that point load of 2450, it was just an imaginary thing. In real life here, this thing is not the point load, this UDL. So that thing of changing the UDL to point load is just there for calculation purposes. But once you draw the graph, you remove that point load, you ignore or you remove that point load, you go back to the original equation. So the original equation in this case is UDL. So there is no point load there. Right. Now this thing here is going to push down or press down. Whatever that you put on top of this beam will be pressing down or pushing down with the magnitude of 25 times 9.81 going down per meter length. So since this force here, whatever that will be here, will be pushing down, or the force of gravity is going to attract it down. There will be a the downward force or downward push. Therefore, we have to go down from here to, we don't know where we're going to end, but we have to draw a line going like this, going down. So we don't know where that line is going to end. Then remember, let's go back to the notes. Yeah, when you read here on the shear force diagram, the portion between 2 points, which is that point, the M and N, you have the UDL there. If you have the UDL, then on the shear force diagram, that UDL will be represented by a downward sloping line. So that's why here I'm not drawing I'm not going to draw the horizontal line. I'm going to draw a sloping line like this. So as long as between this point and this point there is UDL, as you can see on the shear force diagram, you must draw a down sloping line. So now we don't know where this line is going to end. It might go like that to here, or to here, or here, or there. So to find where this line will stop or go, you will do it this way. You will say this amount of force, upward force, minus the total weight of this load starting from here to there. So we want the total load here starting from here up to there. So how to find this total load? So to find this total load, you are going to take the weight per meter length multiplied by the length of this lemon thing that we see there. So the total load will be the weight per meter length. Remember, the weight per meter length will be 25 multiplied by 9.8. Multiplied by 9.8, 145 per meter length. 245. Yeah, so that's when you convert. Remember, this is kg per meter. So you convert that kg per meter to Newton per meter, then you multiply by 9.81. So as I've shown you there from the first notes there, we said that to calculate the total weight of UDL, multiply the weight per meter length by the length over which the load is spread. So to find the total weight of this beam, starting from here to here, or the weight of this green part of the beam, you will see the load per meter length, which is this, multiply by the length from here to there. It's going to be how much? The length will be 8. So the total load of this beam for that green or lemon thing there, for that particular portion, it will be 1960 Newton. 1960 Newton. Then you will say 908.75 minus 1960. I'm trying to, oh, I've opened the wrong thing. I was trying to get the calculator. Right, you will say 908.75 minus that total downward force. It's 1960 equals to negative 1051. Yeah, so now from there you are going to draw a line from here to a value that will represent that negative 10 negative 1051. So this negative is all about the direction, yeah? So this upward part is positive, then the negative is from this line going downward. So from this horizontal line going up is positive. So because of we got the negative answer here, that's why we have to come underneath this length, this line here. Yeah, this point will represent that negative 1051, and I still remember very well 4.25, 4.25. Right, as we are following these forces, at this point we find an upward force. There is an upward force here. So which is this force here? This force is going up with the magnitude of this 1581.25. So it means that this point load, which is direction force, remember point load is represented by vertical line. That means here we're going to draw a vertical line going up since this force is acting up. Then we're going to draw a line starting from here going up. To know where this line is going to stop, you will say negative. Okay, let me go to my calculator. You will see this value negative 1051.25 plus 1581.25 equals to 530. Okay, yeah, maybe that 530 will start from here, maybe today. That 530 maybe will end there. Then you must also name it there, 530 Newton. 530N. Then from there, when you check between this point here, as you move to this side, to the right hand side, between this point and this point, we find the UDL, which is UDL, remember, is the weight. The weight is force. So this force is pushing down. So now we'll have to go down by this total force, by this load here, by this weight. So how much is this weight? You will do the same thing. You will see 245 multiplied by the length of this thing, starting from here to there is 2. So 245 multiplied by 2, 245 multiplied by 2, it's 490. So the total weight of these red things here, what that you see from here to there is, it will be that 490. Then we'll have to go down by 490. Remember on the shear force diagram, where you have, if between this point and this point you have UDL, then we're going to use a sloping line. So here we're going to draw the sloping line. Then we start from here. Where are we going to stop? We are going to stop. You will say 530 minus 490. 430 minus that total weight of 490, which is 40. Then we'll move from here and stop somewhere at 40. It will be somewhere there. So this point will be 40 Newton. From there, at the very same point, we find a point load. Remember, we have a point load here of 40 Newton going down. So here's that force. And that means from here to there, we have to draw a line representing that point load. Remember, point load will be represented by a vertical line. Then we have to draw a vertical line from here going down. So where are we going to stop? So to find that point of stopping, we'll say this 40 minus this 40. We say minus because this force now is acting down. Then 40 minus 40 will give you 0. Then you draw that line from 40 to 0. And that's how that is the shear force diagram. So we've answered question 512. So now let's go to question 5.1.3. Determine the bending moment at the main principal points. At the main principal points. So at the main principal point, we will be referring to where there is a point load, and then we're referring to a point where the shear force diagram crosses that horizontal line. So we have the point load here, and then this point as well, we're going to take it into account. This is a principal point. So we still have this point here, and there we still have point loads. We can still consider them as principal points, but the bending moment at these points, the bending moment at those points will be zero. So as I've written here, bending moment at the end, at the left hand end and at the right hand end, it's zero. So if we omit these two, then we'll only remain with this one point load, and then the other principal point will be where at this point where this shear force diagram crosses uh, that line, this horizontal line. Okay, let's calculate the bending moments. Let's start with this point here. So the bending moment at this point load, I'm going to do it here. Bending moment at point N. No, cancel this one, yeah. So it's just supposed to be P. At the ends of the beam, we have M and P. So bending moment at point M and P will be zero. So now let's calculate the bending moment at point N. So when you calculate the bending moments, remember bending moment is sum of moments of forces to the left hand side or to the right hand side. I'm trying to go to these notes. Yeah. Here we go. A bending moment at any section of a beam is algebraic sum of moments about the section of all forces to the left or to the right. So to calculate bending moment at any point, we are going to apply this definition. Also try to know it or memorize it, since sometimes they might ask you to define the bending moment. So we're going to add sum of moments either to the left hand side or to the right hand side. So when you take moments, we're going to take moments here at this point. So it's either you'll consider the left hand side, this side, or you consider the right hand side. So it's real up to you. You will get the same answers. But we will advise you to consider the side that will have less forces. But in this case, when you check on this side, you'll have this force and the weight. When you check this side, you'll have this force and the weight. So in this case, it doesn't really matter, since you will have equal forces on both sides of N. Right? Maybe let's start. Let's consider. Let's consider this the right hand side. Let's consider the right hand side. So if you only consider the forces on this side of point N, maybe you will be assuming that this thing is like this. So you only consider the right hand side. So when you check on this right hand side, you will have a force of 40 40. You take that force, you multiply it by the perpendicular distance. Perpendicular distance from N to that 40 is 2. Yeah, then if this force is acting down, we use minus. Because it's acting downward, then it's going to be negative. This negative is about the direction. So remember, this force is going to cause this beam to bend like this. So this kind of bending downward, it's a negative direction. Let me go through my notes here. Right, as you can see from my notes here, uh, the force that tends to bend the beam downward will be negative. And then the one that tends to bend it upward will be positive. All right, when you check on this side, it's not only this force, we are not only seeing this force of 40, but we still have the push here. What is a push? Push is a force. We have this push on this side by the UDL. So we will have two forces. We'll have this 40, then this is a force as well. And how much is this force? We've done it before. We took that 245 multiplied by 2. It was 245 multiplied by 2, 490. So we have another push of the magnitude of 490 downward. And remember I said that for calculation purposes, we change that UDL to point load. Then you put that point load at the midpoint. So we're going to draw a force here, which is acting at the midpoint. So this force is going to represent the total weight of this UDL. As I've said, it's going to be that 490. 490. We only change this UDL to point load when we do calculations. So now it means that the weight of this thing, this red thing that you see here, it will be replaced by this 490. And now when you check on this side, you will have two forces, 40 and 490. Then when you calculate the moment, you just take those forces multiplied by the distances. Then now we are not done with calculating the moment, since we are going to have two moments here, since we have two forces. Then other moment will be from that force of 490. So since we'll tend to bend this thing downward or is acting down, it will be minus, then we'll say 490 times the distance from N to that 490 is going to be 1. Remember I said that we put that point load at the midpoint of the UDL. So the UDL is 2 meter, half of 2 meter is going to be 1. So that's why I have 1 there. Then you press your calculator. Hopefully you will have negative 570. Yeah, bending moment, remember, is force multiplied by distance. The unit for force is Newton, the unit for distance is meter. So that's why here you are going to have Newton meter. Okay, no problem. Let's say someone decides to consider the left-hand side. Then you'll have this force acting up will tend to bend this thing upward. You're going to make it positive. Then we're still taking moments at point N, but we're considering the left-hand side. Then we'll have this force at M. So this force at M, it's having the magnitude of 908. 908.75 multiplied by the distance from N to M is 8. And from there you will have a downward force. It's minus 1960 multiplied by, remember that 1960 is from where? Is from changing the UDL to point load. So you just do this, you can see there on the calculation. Then remember, once you change the UDL to point load, you put that point load halfway of that UDL. So the total length of the UDL is 8. Halfway will be 4. So the distance from N to that red force there will be 4, halfway of the UDL. Then you take this, multiply by 4. Equals to, you will get the same answer of negative 570 Newton. So here I was just showing you that whether you consider the right hand side or the left hand side, you will still get the same answer. Right. Now we are here. Before drawing the bending moment diagram, calculate the bending moment at each point on the loading diagram. So we're still doing this part of calculating the bending moment at each point. But remember that other point is where this shear force diagram crosses the 0 line. Now remember, a moment is force multiplied by distance. So at the moment, the challenge is that we don't know the distance from here to there. Then without this distance here, you can't calculate the moment, because the moment, to calculate the moment, you'll take this force multiplied by this distance. So before you can calculate the moment, then we have to find this distance here. So now the question is how to find that distance there. So to find this distance, actually you've got 3 options. But the easiest one, where is that? Okay, here's the statement. To find the position, let me remove these things. To find the position where the sloping line crosses the 0 line, use similar triangles, or just divide the height of the formed triangle from the shear force diagram by the value of the uniformly distributed load. So the simple one, actually I wrote 2 methods, but the simple one that I'm talking about here is this one. divide the height of the formed triangle by what? By the value of the uniformly distributed load. So I'm going to do that now. Right, so to find this distance here, you can see that we have a triangle here. Then this is the height of this triangle. So you'll take the magnitude of this height. Let's say this distance is x. So to find the x, you will say this height of the triangle, which is 908.75 divided by UDL. UDL, remember, is this one. The weight per meter length is 245 divided by 245 equals to, yeah, equals to 3.709, meaning that the distance from here to there is 3.709 meter. Now, since we know the distance, then we can calculate the bending moment. So if you know the distance, then we can calculate the bending moment. But these things like this, if you want to know, let's say the distance from here to there, you will do the same thing. You will just say this height of this triangle, which is 1051.2 divided by the UDL 245. So that distance there 1051.25 divided by 245 is 4.29. So 4.29. So easy like that. So just take this divided by UDL. Yeah, so someone might decide to use similarities. Since this angle will be equals to this vertical opposite angles equal. This is 90 degrees. This is 90 degrees. And this angle will be equals to this angle, alternate angles equal. So since all these angles equal, then we can use similar triangles. So similar triangles, the ratios of the sides of these two triangles will be equal, meaning that the ratio of this side to this side will be equals to the ratio of this side to this side, or any side. You can just take any side, divide by this side. Make sure that you do the same thing on this this other triangle. Then now I decided to take this vertical side divided by this horizontal side. 908 divided by horizontal side. Remember, this horizontal thing stands for distance, the length of the beam. Right, you take that 908 divided by horizontal is x. At the moment, remember, it's just an alternative of calculating x. We assume that we don't know x yet, so it's alternative. Then we take that, we equate it to, we come to this, we say this vertical side divided by horizontal side. So the vertical side from here to this 1051.25 divided by this side, which is the distance. Remember the distance from here to there is 8 meter. So if from here to there is 80 meter and then from here to there is x, then this length from here to there will be 8 minus x. So this distance is 8 minus x. Then we divide by that length of 8 minus x. Then from here you cross multiply, or you do whatever that you can. You can say you multiply by LCM both sides. It's up to you. Then you make x the subject of the formula. Then you will remain x will be equals to 3.709. So now once we know the distance here, now we can calculate the bending moment. Now we can calculate the bending moment. Right, now since we managed to find the distance where this shear force diagram crosses the zero line, then we can come back to this load beam diagram. Then now we're going to find the bending moment here at this red line, which is located at that distance of 3.709. So we're going to check this side, the left hand side. When we check the left hand side, you'll have this force here and then this blue force, which is the weight of that beam starting from here to there. And then the weight of this beam starting from here to there will be equals to this 245 times the distance, which is this. So this brown arrow though represent the weight of this blue thing there. So now when we check this side, you will consider this force and this force. That blue thing is represented by that brown force. So we will consider this black force here and then that brown force. Then we'll just have to take those forces, multiply them by their distances. You'll have this upward force is positive since it will bend this thing upward. And then it's how much? 908. 908.75. That is direction at M multiplied by the distance from this red line. Remember we're taking moments here on this line. So the distance from here to there is 3.709. This red line here, I just gave it with the position of this red line is x. That's why I said that the bending moment at point x. So point x is referring to that red line there. So the distance from x to that force will be 3.709. 3.709 minus there is that downward force, minus that downward force, total force is 108 times 705 multiplied by the distance from that red line, which is x, to that brown line, that force there. So that the distance will be half of 3.7. So half of 3.7 is 1.854. So you can quickly press the calculator there. Right, that's what you will get. 1685. Comma So that is the bending moment at x, which is going to be our maximum bending moment. Remember, the main reason of drawing this shear force diagram is to find the point where we're going to have the maximum bending moment. So from this shear force diagram, this horizontal line crosses, this shear force line crosses this horizontal line here and there. So it means that here or here, that's where we're going to have the maximum bending moment. So this is where this beam is going to bend too much. Then if that bending is more than the ultimate bending moment of that particular beam, then particular material, then this beam is going to break there. So by drawing this shear force, actually, we are trying to find where this beam is going to fail due to bending. So we're trying to find where this beam will bend too much compared to the other parts of the beam. So it will either be here or here. And then you just have to calculate the bending moment for here, bending moment for here, then you compare the two values. So if the big value is from here, then the maximum bending moment will be here. When you compare the values, you must ignore the sign. Remember, the sign is up, it's about the direction. Right, after calculating the bending moment, then we come to bending moment diagram. And I've said that one of the principal points, it's the point where this thing, the shear force diagram will cross the 0, 0 line. So the shear force diagram will cross this horizontal line here. It means that this point is one of those critical points. So it's one of those principal points. So you draw a dotted line like that. And now remember we said that the bending moment at point the M at the beginning it's 0. Bending moment at this point as well, at the end it's 0. Now you will go to bending moment at the point the X. Bending moment at point X, we said is positive 1685. Let me erase this thing here. Then you will come somewhere here, maybe somewhere here, this point here at point X. We said that the bending moment is 1685.36. Right. From there you go to point N. Point N, we said that the bending moment is negative 570. Because of that negative, this is point N here. Because of that negative, we come below this horizontal line. We said that the bending moment it's negative 570. Right, from there, what is remaining now, we just have to join these points. We join this, we're going to join this point here and this one, join this one and this one, join this one and this one. Right, on the bending moment diagram, on the bending moment diagram, I'm on this point here. The portion between 2 points carrying UDL will be represented by parabolic curve, by a curve. So since between this point and this point, which is this point and point X, there is a UDL there, and to join this point and this one, we are going to use a curve, parabolic curve. The same thing throughout here between this point and this one, this part here, there is UDL, you will use a curve. Between this point and this one is this one here, there is UDL. We're going to use the curves to join this point. Right, those curves, when you put them here, we will be guided by this thing. You just have to check from the shear force diagram. On this part, or this part here on the shear force diagram, you will see this triangle here. So that triangle, which is the same as this, above that horizontal line is the same as this. So because of this triangle, which is like this, then it means that when we join this point and this one, we are going to use a curve uh, in this manner. Our curve will be drawn in this manner. It will go like this or like this. So meaning that from here to there, our curve will go like that. So it will be something like this, like that. And then now you check between this point and this point, as I've said, that there is a UDL. You are going to have this triangle here below the horizontal line, and it's like this. As you can see, that triangle is like this. Then we're going to join this point here and this one here using this kind of curve, and we're going to join those points with this kind of curve. Good. Then from there you come to this portion here. here there is still uniformly distributed load. Then you go to shear force diagram. When you go to the shear force diagram, you will have this triangle here. This triangle is above the horizontal line, and that triangle is like this. It's taking this kind of shape, that triangle. So because of that, then our curve will go like this blue one. It will be like this blue one. So we're going to join this point and this point with this kind of curve. Good, that's all. That's how our shear force diagram will go. Make sure that you label it or you indicate the values as I've indicated on the bending moment diagram and the shear force diagram. And then lastly, where this bending moment diagram crosses the 0, 0 line or the horizontal line, at this point we're going to call it inflection point. Inflection point. Let me say inflection point, IP. What is the inflection point? So as you can see here, at this point it means that there is no bending moment. At this point, bending moment is 0. So at that point where the bending moment is 0, that point we call it inflection point. Then when we construct this thing, beams, when we join them, that's why we're going to make a join. So that's why we're going to make a join there. Yeah, as you can see here, inflection point is the point at which no bending moment occurs. Right, when I check here, we've answered all questions. And then it's advisable as well not to make calculations below the load diagram. So below the load diagram, we prefer to see the shear force diagram and the bending moment diagram. So when you do calculations, I advise you to do calculations uh, on the separate page. Don't do your calculations below these things. But it's not a must. But from most of us or the authors, they prefer it in this way as I've done it here. Yeah, thank you very much. Hope to see you in the next lesson. Thank you.